All right, another video, another related rates example. This time, we've got an oil tanker that is leaking oil in a radius around the ship. So, okay, here's my oil tanker. It's perhaps not a very good oil tanker, it's just a sailboat. And it is leaking oil in a radius around the ship. That sounds bad. So here's leaking oil in some radius around the ship. So here's my radius, we'll call that R. A helicopter monitoring the ship measures the radius of the spill to be increasing, at 0.32 feet per minute. And I'm going to really emphasize 0.32 feet per minute. Per minute in particular. This is a rate. So this is a rate. This is not R. This is how the radius of the spill is increasing. So instead of R, that is actually dr over dt. That is 0.32. We said it is increasing, so it should be a positive 0.32. And actually, let's write our information over here. The picture isn't critical in this, but I think it's helpful. dr over dt equals 0.32. It says find the rate at which the area of the spill is growing when the radius is 500 feet. So my radius is 500. So R is equal to 500. What do we want to know? We want to know find the rate at which the area of the spill is growing. So the area of this shape that I've drawn right here. So essentially I need the area formula for a circle. So if you don't know that would be handy for this problem. I need area of a circle, which is A equals pi r squared. That would be a good one to memorize. So I don't know A, but remember we said in the last video it might be okay. We might not need to know A. The thing I'm really looking for, though, the thing I want to answer, find the rate at which the area of the spill is growing. So I want to know what is dA over dt. This is what I'm after. This is what I'm looking for. So I have this relationship between my area and my radius. I'm going to go ahead and take the derivative with respect to time. So the derivative of A, that's going to be 1. But remember, we are taking the derivative implicitly. So I want to make sure that I multiply by the implicit derivative of A with respect to time. I think that writing in that d over dt can be particularly helpful. So I want to multiply 1 by dA over dt. That's the rate of change of area with respect to time. Equals over here, it might look like we need a product rule right there, but remember that pi is just a constant. Pi is 3.14159, and then it continues on forever. So that's just a constant, so that means this right-hand side really just needs a power rule. So I'll multiply by my power, 2 times pi times r, but I'm taking the derivative with respect to time, so I'm going to multiply by the derivative of r with respect to time, dr over dt. At this point, I can't really simplify this anymore. Finding the derivative wasn't too bad. I'm going to take what I know over here, dr over dt and r. I'm going to plug that in. I'm going to see if I can get a solution here. So dA over dt is 2 times pi times r. We said r was 500 times dr over dt. dr over dt is 0.32. And if we multiply this out, I should have, I believe, 320 pi. 320 pi. Let me just double check. Yep, 320 pi. Or, if you wanted to round and give a decimal approximation, I believe it's 1005.31 if I round to 2 decimal places. So I want to make sure that I give a units, and then I want to check to make sure that the sign of this answer is correct, that it makes sense for our problem. So 320 pi, again, you can work with either one of these. It doesn't really matter which one. I'll work with 320 pi. Remember, we were looking for the derivative of area. So what are our units of area? So our unit for the radius was 500 feet. So 500 feet. But we don't use feet to describe area. We instead use square feet. So I'm going to say 320 pi feet squared per, what is my unit of time now? What is my unit of time? Earlier we said feet per minute right there. So that means my unit of time is per minute. So my answer, 320 pi feet squared per minute, or 1005.31 feet squared per minute would be my solution. And again, you may just want to double check. Does that make sense? Think about what's happening. Our radius is getting larger as time goes on. So later on, my radius might be all the way out here. Do I have a larger area or a smaller area? Well, the area of the red circle, or part of the circle that I've drawn, is larger than the area of the blue circle. So yes, that makes sense that our derivative is positive because the area of the spill is increasing over time. So here we go, that's our solution. I think that this problem is much more approachable. It's a little bit easier to follow. So this is a good example to follow up that first one if you want to find something that's a little bit easier and more approachable than our first problem.